So the problem that we're working on today is there's a pair of rods that are suspended from the same pivot point, and they're different lengths and they're different masses, and you release them and they hit each other at the bottom and they stick together, and then they'll go up on one side, and you're supposed to find the angle that they go up to. Now there's a little bit of trickiness in terms of when you have to release them to get them to hit right at the bottom, because the problem does specify they hit at the bottom.
Okay.
And that's your zero angle. But all that's sort of behind the scenes stuff, and you don't actually have to worry about it in the problem. How would you guys think about approaching this problem?
I would probably try to use conservation of momentum. That would be my first instinct. Treat them as two systems at the beginning, and then after they hit, treat it as an inelastic collision, and then try to figure out how high they'll go from that.
Okay. Yeah, and at that point, then use conservation of energy to see how high it swings from its kinetic energy into its potential energy.
Tell me a little more about why you're picking those.
So I feel like I'd pick momentum because it almost seems like a classic thing with them sticking together at the end, and you have two things at the first, and each one has some velocity, and then they'll hit and their masses will add and they'll be moving at one velocity, and it almost just seems like setting up the equation in my head to just work. So it should work out.
Yeah, it seems just like the classic ballistic pendulum.
Okay.
So we're gonna have an inelastic collision, so we can't use conservation of energy. And so just the next thing I think to go to is momentum. And then if you have something swinging up, then energy is conserved. And so it seems just like, again, the ballistic pendulum two-part problem.
Okay. So we've got one part for the collision and one part for swinging up afterwards. Mm-hmm. Now they give us that the bars start from rest at the top. And it gives us the masses and the radius of the length of the bar. But it doesn't give us how fast they're going at the bottom, so we have to find that too. Do you think that's just going to be a reversal of the energy for going up, or is there going to be another trick to it? Or
so they're both starting from rest, but are they starting from the same height? Like, are we just assuming
they are starting from the same height?
Yeah, we're assuming that they collide at the bottom.
Right. So here's the trick. One of the bars is a certain length, and the other bar is longer. Mm-hmm. So they're going to hit each other like that. Mm. It's not as if we have like the Newton's cradle pendulum with the balls on the ropes and they clack into each other, right? It's not like there's just one point of contact for it. It's along the whole surface.
Right.
Okay.
But it does specify that they're hinged together at the top, and they start horizontal. And you got to send the shorter one down later, because it takes longer for the longer one to go down. So you start that one down, and then you release the shorter one, and they hit at the bottom. And
so could you use angular momentum to do that
instead of regular momentum?
Yeah.
Okay. Why do you say that?
Just because you are using a solid rod, so you would want the moment of inertia, and it seems like the angular velocity would be more useful than the linear velocity.
Okay. So we've got three parts. I'm just sort of keeping track of things for us here. We have the initial part where we're going to use conservation of energy. We have the collision after they hit at the bottom, or while they're hitting at the bottom, that we're saying we're going to use angular momentum for, and then energy again as it rises up after that. So
could you just use angular momentum instead of energy and angular momentum? I was thinking like angular momentum for the whole first part, like for the first and second part.
Okay. What do you think about that?
When it's at rest at the top, it doesn't have any angular momentum. So it seems like you want to start considering the angular momentum after it is moving, and then have that be conserved.
Yeah, and I think you've hit on something there where if we use angular momentum, we want to deal with a conservation kind of situation, or something where we can define an angular impulse. Regular impulse is integral of force over time. Angular impulse is just integral of torque over time. And our problem here is that the torque would be changing continuously. You have gravity pulling down on it fairly well at the beginning, but as it swings down farther, when it's down at the bottom, gravity's pulling down, our radius would be down, so we'd get no torque. And so the torque is actually changing throughout the whole swing.
Okay.
So it seems like energy is probably going to be an easier thing to use. I'm sure you could do it with angular impulse, but you might need some better calculus methods than we have in this class to handle how the torque changes over time.
So why doesn't it just have zero angular momentum at the beginning and then some angular momentum at the bottom when it collides?
It does, and that's our problem.
But it's based on the torque changing.
Right.
Okay.
We'd like to have a conservation setup if we're using angular momentum. If we can't have a conservation setup, we need to be able to find the angular impulse easily, and that's not something we can do very easily in this situation. So for the energy, what would you use for, you said it was all potential energy at the beginning. Potential energy is mass times gravity times height. What would you use for the height?
The length of the longer rod. Sort of the total distance that anything's going to travel. Like that's the highest and the lowest point. It's going to be the two ends of the longer rod.
But what about the shorter rod? Right, the longer rod, the end certainly goes that far, but the shorter rod is only half as long in the problem.
Oh, right. So the problem is that when it gets to the bottom, it should be all kinetic energy. But if we define that as the height, then that means it still has potential energy at the bottom when it's swinging.
Yeah, I mean, we can always have potential energies be different at top and bottom. It's the difference in them that matters.
Yeah.
So you want to use the length of the rod for each one?
Yeah.
Okay. So now if we look at, say, the longer rod, the end of the rod definitely falls a distance equal to the length.
Mm-hmm.
What about the stuff up near the top?
So assuming that the mass is uniformly distributed,
Which it is.
I don't know how to put this the right way. We can find like some average.
Center of mass?
So yeah, so it's how far the center of mass falls, right?
That seems like the right approach. You'd want to find the center of mass and do everything in terms of the center of mass of the two rods.
And if they're uniformly distributed, that the center of mass is just half
In their middle.
the distance.
Right.
And so half the length is the height for each of them. Oh.
Okay. So once you have that, you have potential energy to start with. Now we know what that is in terms of the quantities we've been given. Now we need to have the final energy just before they're hit. How would you go about finding that?
You just set it equal to, set the potential energy of the rod equal to its angular kinetic energy.
Okay, so 1/2 I omega squared, that sort of thing.
Could you do it with like the linear speed of not the linear speed, but just the regular half mv squared of the center of mass?
So I tried that and I ran into a problem with that because I thought, I'll just do all this in terms of regular velocity. And the problem that I ran into was because there's a v squared there, the stuff that's at the end of the rod, which is moving faster, has a more than linear increase because of the v squared.
Okay.
In terms of counting up the energy, and that turned out to be a problem. Now it's also nice because if you do it in terms of I and omega, then you have I omega all the way through, and you can use that to do some cancellation later, and some easier substitution than having to go back and forth from angular velocity and linear velocity.
Yeah, okay, that makes sense.
But that's sort of a nice thing on the side. Treating it as if it's just the center of mass moving with the center of mass's velocity shortchanges the end of the rod in terms of its energy. Okay, so we're turning gravitational potential energy into rotational kinetic energy.
Mm-hmm.
So that should handle us for step one. Step two was going to be angular momentum for a collision. Is there anything that you guys think we should watch out for there?
Well, so the center of masses are in different places. Oh, you'll have a new center of mass.
Yeah.
That's all.
Yep. And you can take all that into account by finding the new moment of inertia for after they hit. So you'll have two different moments of inertia beforehand, and then you'll have a new one afterwards.
So we can find the moment of inertia without finding the center of mass?
Basically, yeah. All of that is sort of hidden behind the scenes in terms of the calculation. Moments of inertia do add together as long as they're around the same axis. So we don't have to worry about any kind of funky, they don't add properly thing.
Okay.
They do add just fine.
Good.
And then after that, the whole thing will be swinging up. How do you think we can find out the angle that this thing goes up to?
Just do the opposite of what we did in the beginning.
Okay. What height are you going to use when you deal with potential energy?
We should use the new center of mass height.
Okay.
Yeah.
And that's probably the more efficient way to do it. I ended up just taking the two rods individually and saying, okay, they're at the same angle. Let me look at their individual heights, get an individual potential energy for them. And it probably would have been nicer if I found like the center of mass.
Sure.
But it did work out.
Awesome.
So was that last part particularly messy?
For me, the whole thing was kind of messy. You need to be really detail oriented in this problem. You've got two different moments of inertia to keep track of for two different objects that have, they both have a mass with m in it and a length with l in it, right? So one of them is m and l and the other one is 2m and 2l. And so you end up with a lot of extra little factors of 2 to carry around. And if you're not careful about keeping track of all that detail, you end up taking 6 or 7 attempts on the problem like I did, where every single one you go back and sort of revise it. It is a little bit messy in the end. It's not one of those problems that comes out to, oh, it's 30 degrees. You know, it's not that easy. You know, you have to take an inverse cosine at the end because you have to figure out the angle based on the length and all that. So it's sort of a messy answer.
Sure.
It's something where it really pays to keep track of every tiny detail and to go over it again before you enter an answer.
So how did you realize that your first few attempts came out with the wrong answer?
I knew I had the right approach. Like all the stuff that you guys were talking about were things that I based my approach around. But you know, I put my answer into Lon Kappa and it said incorrect. And I'm like, okay, what now? And so I go back to it and tried to find at least one place where I had an error, and went through and recalculated everything and put it in, and I got incorrect again. And so I went back and found another error. And the first time this happened was very misleading for me, because I had a very complex and nasty looking expression. I'm like, well, it's sort of a mess, but these problems are tough, so let's try it. I got the wrong answer, and I recalculated and put things in again, and I got this very nice looking answer where I got like an inverse cosine of 24 over 25. I'm like, wow, that's so much better. Like, that's way easier. Oh, it's wrong. Oh. And the final answer that I came up with was about as messy as the original one that I started. But it took a lot of sort of messing with the details.
And do you have any tips for how to recognize that going into the problem?
I think that anytime you're given a problem where you're expecting to see some information and it's not there, like for this one, I was expecting to see like the times that it initially got dropped at. You know, without being given that, it really made me think about how I'm going to set it up properly at the beginning, so that I will never need that information. There was another one this week, which we'll go over later on, hopefully, that you would think you'd need the coefficient of friction to solve it. I think that in this one, because we're dealing with a couple of different concepts put together, and it's a 3-part problem where each part needs the previous part, that's also a good indication for me. Anytime you've got multiple steps that need to be fed into the next step, that's definitely a time where you need to keep track of things at every step along the way.
A lot of times in physics problems, they'll say, like, assume they have these multiple objects have the same mass, or the same this, or the same that. The fact that you're dealing with two objects that have different masses and different lengths.
Yeah, that's a good point.
That probably also kind of hints that this might be a little messy.
Mm-hmm. Yeah, I can imagine if we had the ribbon problem and they had different masses, that would have made things more tricky.
But just more messy, not less doable.
Right. It's certainly the same problem at the gut, you know.
Sure.
So is this a sim problem?
I think this one really lends itself well to that approach. I think that it's easy to define your system. Right? You've got the two bars. Not much else going on in this. I think that, you know, for the first part, you need each of their velocities individually, so it's easy to pick out the fact that you need the two of them separate as a system, and then together for the collision, and then together again as they swing up because they're stuck together. I think that you guys picked out the interactions fairly easily. The fact that there's a collision that you were talking about, and then sort of behind the scenes talking about the potential energy with gravity being involved. And then the model for this, I guess, is what we started with, saying how would you approach it. So I think that this problem lends itself really well to that sort of approach.